In this problem, we've got a disk attached to an arm, and that arm itself is rotating around an axis, as you can see. Now, there is another solution to this video, and in that solution, a particular approach was taken. That is one possible way to solve the problem, but I'm about to show you another possible way to solve it. Before we start with the new solution, let me remind you what the other solution looks like. So let me go ahead and remind you of what that one is like. So I'm going to start here using red, and in the other solution, the rotating axes are attached to the arm OB. So the axes are here, X and Y, and the observer is attached to arm OB. So the equations I'm about to write in red are the ones that are for the original solution to the problem. So the red set of axes and observer are attached to the arm OB. And if you watch that other solution, you've already seen how this turns out. Basically, omega turns out to be omega 2 in the capital J, and minus omega 1 in the little I, and we can write alpha after a bit of work. This just turns out to be omega 1, omega 2 in the capital K. And then from there we can go ahead and write the velocity of point A and the acceleration of point A. Velocity of point A turns out to be a couple of terms in the K direction that I'm going to collect in a second. First, it's minus R omega 3 in the I direction. And then to that, we're going to add two terms. Turns out it's minus B omega 2 and then R omega 1 in the K. And then if we want to write the acceleration at point A, we're going to get a bit of a longer expression. It looks like this. Minus B omega 2 squared minus 2 R omega 1 omega 2. That's all in the capital I direction. Minus R omega 1 squared plus omega 3 squared in the J. And then to that we add plus 2R omega 2 omega 3 in the K. So that's the existing solution. And what we're going to show you now is that there's another way to get that same solution. It's a slightly different approach, but of course the velocity and the acceleration turn out to be the same, even though omega and alpha are going to be different. So for this part of the solution, I'm going to go ahead and use black. So anything that you see in black here is going to correspond to the solution, where I'm going to put my axes in the same place, X and Y, but I'm going to attach my observer out here to the disk. So the axes attached to the disk, and I want to be explicit here that those axes are at point B, and those axes are rotating with the disk, meaning that those axes are rotating with omega 3. Okay? And so the question is, how does this change the process? How does this change omega? How does it change alpha? Let's just go ahead and get right into it. Let me move down a little bit. Keep the picture on the screen so you can see it. Let's just start by writing omega. So omega now has three pieces to it. Omega has omega 2 in the capital J, minus omega 1 in the little I, plus omega 3 in the little k. We'll leave it just like that for now. We'll come back and address the mixture of coordinates there in a second. Let's go ahead and look at alpha. So alpha then is going to be the time derivative of omega, So we're going to get several terms out of that. So we've got omega 2 dot j hat plus omega 2 j hat dot. We get minus omega dot in the I minus omega 1 I hat dot plus omega 3 dot in the k plus omega 3 k hat dot. The information that we're given tells us that these omegas are constant, so all the omega dot terms are going to go away. So that one goes to 0, that one goes to 0, and that one goes to 0. We know that J, capital J, is the fixed coordinate, so we know that one goes away. And what we're left with are these two terms here that we have to deal with. We're going to go ahead and rewrite those. So we get minus omega 1, and then the time derivative there is omega crossed with I, and then to that we're going to add omega 3, and that k dot becomes omega crossed with k. So there's a bit of algebra that we have to do here in order to sort this out. We make a little room, and this becomes minus omega 1, and then here we just insert omega, so we've got omega 2 in the j minus omega 1 and a little I plus omega 3 in the k, and that's crossed with I. And then to that we add omega 3 and the same thing. Now we've got omega, so that's omega 2 in the j minus omega 1 in the I plus omega 3 in the k, and that's crossed with little k. So when we go ahead and we get all of those things worked out, we end up with an alpha that has two terms to it. And recognizing that at this instant the little ijk and the big ijk are lined up in space, we can go ahead and write alpha as omega 2, omega 3 in the big I, and plus omega 1, omega 2 in the big K. Okay, so let me just take a quick moment to remind you of how those are different from the previous example. So in the previous example, I'll scroll up to show you. The previous example, omega had just two terms. For the axes attached to the disk, there are three terms. Alpha had just one term, and for the axes attached to the disk, you can see that alpha has two terms now. And so the relative merits of attaching the axes to the disk, so far the price to pay is that we've got an extra term in omega and an extra term in alpha. And the question is that a good thing or a bad thing? Well, let's let the solution unfold and see how it goes. So from here, now that we've got omega and alpha, we can go ahead and write some velocity equations. So let's go ahead and see what we get. So I'm going to write velocity of A is equal to the velocity of B plus the velocity of A relative to B, and I'm going to write that as omega crossed with R of A relative to B. Now the question is, why can I write it that way? Why have I not included the terms that you see in the other solution? The terms like, and I'm going to do this in red because it corresponds to the other solution, there's a term like velocity of A relative to B relative. I've not included that here, and the reason is that this term kind of takes up all of that relative motion. Remember that A and B are now on the same rigid body. So let me go back up to the picture to show you that. In this case, the axes, the black axes, are at point B, but they're rotating with the disk. And so now A and B are on the same rigid body. And so all of those velocity of A relative to B rel type terms, those are going to kind of go away, and we can capture all of that relative motion just with that omega cross RAB term. All right, so that's why we've got that. Let me go ahead and expand this out and show you what the rest of this looks like. So velocity of B, that just turns out to be omega 2 crossed with the vector from B back to O. That's B in the I direction. And then we're going to go ahead and expand omega. So this becomes plus omega 2 in the J minus omega 1 in the little I plus omega 3 in the K. crossed with r from b up to a. That's the radius r in the little j. And so when we go through and we kind of sort all that out, we get velocity of a turns out to be several different terms. Let me write this as minus r omega 3. Again, keeping in mind that the little ijk and the big ijk are aligned at this instant in time. We get that term, and then to that I'm going to subtract two terms. There's a b omega 2 plus r omega 1, and that's in the k direction. Right? So there's my velocity of a. Let's go ahead and check that and make sure that that is the same as the solution we got when we looked at the red axes. It's like I'm not going to get them on the screen together. But there you go. You can see that we've got the two terms composing the k part and the one term in the I part, and everything looks like it is the same. So that's pretty good so far. Now let's go ahead and do the same kind of process and see what we get for the acceleration. So for the acceleration of a, we're going to write that as the acceleration of b plus two terms. One is an alpha crossed with r kind of term, and the other one is going to be an omega crossed with omega crossed with r term. Okay, now again, because these are on the same rigid body, meaning points A and point B are on the same rigid body, we can capture that relative motion just with these two terms. The alpha and the omega are the alpha and the omega that we worked out above, as you can see right here. And the r from A to B is the same r from A to B that we worked out right there. So now all we've got to do is figure out what's going on with the acceleration of b, and then go ahead and propagate the algebra through and see what we get. Well, the acceleration of b is going to be the acceleration of O plus the acceleration of b relative to O. Let me go back up to the figure to remind you of where O is. So O is back here at the root of the arm. And since we know all the omegas are constant, we know any alpha term is going to go to 0. So if we write this term right here as like some sort of alpha 2 crossed with r of b relative to O plus omega 2 crossed with omega 2 crossed with r of b relative to O. We know that term's going to go away because alpha is 0, and we're left with just the omega cross r term. In terms of the acceleration of O is really a stationary point, so that one goes to 0. So this whole thing can just be written as the omega cross r term, and we can show that that turns out to be minus b omega 2 squared in the capital I direction. Again, taking advantage of the fact that the big I and the little I direction are the same at this instant. So what remains then is to calculate these two terms. Go ahead and do the algebra and see what we get. So let's go ahead and start there. Make a little room here. Let's start with the alpha cross r of a relative to b term. This is going to be alpha is omega 2, omega 3 in the I direction, plus omega 1, omega 2 in the k direction. And that's crossed with r of a relative to b, and that is the radius r in the little j direction. Again, we're going to take advantage of the fact that the I, j, k axes, both the big and the little, are aligned at this point. And if we go through the algebra here, we get minus r, omega 1, omega 2 in the I, plus r, omega 2, omega 3 in the k. So that's that term. And then the omega cross r of a relative to b term is a little bit more work. Let's go ahead and see if we can write this out. So let me write it this way to save a little space at this point. It's going to be omega crossed with, let me write out omega so we can do the second part of the cross product there first. The omega is omega 2 in the j minus omega 1 in the I plus omega 3 in the k. and that's going to be crossed with the radius r in the j. So just this part of the cross product, this turns out to be, let's see here, minus r omega 1 in the k minus r omega 3 in the I. So now the second part of that, where we take omega crossed with that term, if we turn the crank on that, the algebra gives us a number of terms that are going to kind of come together. So let's go ahead and have a look at those. So that omega cross r term, when we add it all up, turns out to be minus r omega 1 omega 2 in the I, let's see, minus r omega 1 squared plus omega 3 squared in the j, plus r omega 2 omega 3 in the k. And that's our omega cross r term. So once we collect all these terms together, that would be the term from this part of the equation, and the term from the alpha cross r terms, and then the term down here from the omega cross r term. Let's collect those all together. And the acceleration of A then turns out to be minus b omega 2 squared in the I. That's the acceleration of B part. And then we have this collection of terms from the alpha cross r and the omega cross r. So let's go ahead and substitute those. So from the alpha cross r term, we have minus r omega 1 omega 2 in the I, plus r omega 2 omega 3 in the k. And again, this is the alpha cross r part. Then to that, we're going to add the omega cross r part. So that's minus r omega 1 omega 2 in the I hat minus r omega 1 squared plus omega 3 squared in the j, plus r omega 2 omega 3 in the k. And that whole thing is the omega cross r part of this. And then all we have to do is collect all those terms and write them in a reasonably convenient form. So let's collect the I, J, K terms. We're going to get acceleration of A turns out to be minus b omega 2 squared minus 2r omega 1 omega 2. That's all in the I direction. And then to that we have minus r omega 1 squared plus omega 3 squared in the j direction. And then to that we add 2r omega 2 omega 3 in the k direction. And there is our acceleration. Now let's go ahead and check that. Let's compare that with what we wrote for the red axes, which was the other solution to the problem. If I scroll back up, you're going to see that indeed we get the same thing that we got for the red set of axes. So the point of this is that you can use either set of axes that you want. There are pros and cons to each. For the red axes, you saw that omega and alpha are reasonably straightforward to write, but the velocity and acceleration equations are perhaps slightly more complicated. For the black axes, the ones that are attached to the disk, you see that omega and alpha are a little bit more difficult to write, but the velocity and acceleration equations are slightly simpler. They have fewer terms in them. Both of these solutions involve a bit of algebra that you have to be careful about, but in the end, you get back to the same set of equations for the velocity and the acceleration.